In the previous video, we expanded on the use of stoichiometry by introducing limiting and excess reactants. Today, we're going to conclude Unit 3 as we discuss reaction yield. We already know that not all reactions react cleanly due to the influence of limiting reactants. Oftentimes, there are reactants which are not completely consumed in a reaction, and these leftover substances are termed excess reactants. We've also familiarized ourselves with the reactant method and the product method, both of which are used to determine limiting reactants and the identities and amounts of excess reactants. Our focus today is on the yield of reactions. The word yield in any context refers to how much is produced relative to how much is needed to produce said amount. We can return to our cooking analogy for this. Most recipes will specify a yield, telling us how many servings of a dish a particular combination of ingredients will give us. Chemists are interested in yield too, since we've already established that chemical reactions don't usually follow the rules of ideal stoichiometry. Just because a chemical equation tells us that a reaction will produce however many moles of product, doesn't necessarily mean that the predicted number of moles will be produced. In many cases, a real-life reaction doesn't produce the amount of product predicted by its corresponding chemical equation. Reaction yield helps us quantify this. We define reaction yield as how much product can be made relative to the mass of reactant consumed. Another less technical definition is that it measures the efficiency of a chemical reaction. This will become a lot more clear once we look at our example problems. Reaction yield itself is most often expressed as a percentage, and when we express reaction yield as a percentage, we call it the percent yield. Down here we have the formula for calculating percent yield. Percent yield equals the actual yield divided by the theoretical yield multiplied by 100. Let's define these terms. The actual yield is the amount of a particular product obtained from a chemical reaction in a laboratory setting. We're talking about real-life chemical reactions, not the sort expressed by chemical equations. Picture a chemist in a lab mixing chemicals together and trying to obtain some new chemical. How much of that new chemical is produced is the actual yield. On the other hand, the theoretical yield is the amount of a product that should theoretically be obtained from a chemical reaction according to the corresponding chemical equation. In other words, the actual yield represents the real-world result, telling us how much product is actually produced when the reaction is carried out using real chemicals. The theoretical yield tells us how much product would be produced in an ideal scenario. We come back to a common theme here. Real life is rarely ideal. Chemical reactions don't always produce the amount of product their equations say they'll produce. Because of this, the actual yield is usually lower than the theoretical yield. It can hypothetically be very close, but the actual yield will never be greater than the theoretical yield. It wouldn't make much sense if it were possible to make more product than the ideal amount of product. Actual is always lower than the theoretical. The theoretical yield amount would be obtained if the limiting reactant was completely consumed in the reaction. Now, this might be confusing for some viewers, so let me explain this a little more. Yes, the limiting reactant is the one that ends the chemical reaction when it's completely consumed. This is what we established last time we were here. But if the limiting reactant is always completely consumed, shouldn't every reaction be ideal and happen according to the corresponding chemical equation? We might think so looking at this, but the reality is different. Reactants in a chemical equation don't always produce the products we want them to produce, and we'll talk about this when we get to Unit 7. For now, though, we can say that there are usually more than one set of products possible for a combination of certain reactants. This means that if substances A and B are combined, they can produce either substance C, which we want, or substance D, which we don't want. When we calculate the percent yield of C, we'll find that it's less than 100%, since some of the reactant is becoming substance D instead. This scenario is usually referred to as a parallel reaction, and it's a major concern in any kind of chemistry carried out on either a small or large scale. but that can wait until Unit 7. For now, let's start on our first example. Example 1 says, a chemist combined 32 grams of hydrogen sulfide with 17 grams of sulfur dioxide. The reaction produces elemental sulfur and water. If 6 grams of water are produced, calculate the percent yield. Our first step is always to write out the chemical equation so we know exactly what's going on. We should know that hydrogen sulfide is H2S and that sulfur dioxide is SO2. Elemental sulfur is just the element symbol S, and water is H2O. Now we need to balance this equation. I'm not going to go through the entire balancing process since we've discussed it quite a bit throughout this unit, but we can use either trial and error or algebra to put a 2 in front of H2S, a 3 in front of sulfur, and another 2 in front of H2O. That's our balanced equation. Now we go through the stoichiometry. We turn the grams of reactants into moles of reactants using the molar masses. The molar mass of H2S is 34 grams per mole, and that of SO2 is 64 grams per mole. We obtain 0.941 moles of hydrogen sulfide and 0.266 moles of sulfur dioxide. We now need to determine the limiting reactant. We'll multiply both these mole values by the corresponding molar ratios. The molar ratio between water and H2S is 2/2, or just 1. So hydrogen sulfide produces 0.941 moles of water. The ratio between water and sulfur dioxide is 2/1. So sulfur dioxide produces 0.532 moles of water. This is all according to the product method. Since sulfur dioxide produces less water, it's the limiting reactant, and we will use 0.532 moles of water as our basis of calculation for our next step. What is our next step? Our next step is to find the theoretical yield per the chemical equation and the ideal stoichiometry we've just engaged in. All we need to do is convert 0.532 moles of water into grams. The molar mass of water is 32 grams per mole. So we end up with 17.024 grams of H2O as a theoretical yield. This is the ideal yield, the amount we would end up with if everything proceeded according to the chemical equations plan. Our actual yield is provided in the problem, and it is 6 grams. The percent yield is therefore 6 divided by 17.024 multiplied by 100. The final answer is about 35%. Not a very good yield, honestly. Either something went wrong while we were carrying out this reaction, or maybe the reaction itself isn't the most efficient way to produce water. Most likely the latter. So then, this problem essentially encapsulates all the steps needed to find the percent yield given the amounts of reactants and the amount of a product of interest. We do the ideal stoichiometry needed to find out the theoretical yield in grams. And then we divide the actual yield in the problem by the theoretical yield we calculated with all this work right here. That's really why this problem took so long as it did. Finding the theoretical yield requires us to go through all the stoichiometry. There's no way to calculate actual yield, of course, since actual yield is the amount produced in a real-life chemical reaction with real chemicals. That's the difference between actual yield and theoretical yield. Only the latter can be found out using pen and paper. Now for our next problem. Example 2 tells us that the non-steroidal anti-inflammatory drug, known as aspirin, and acetic acid are produced via the combination of salicylic acid and acetic anhydride. A handbook states that 86% is a typical yield. If 2,668 grams of salicylic acid are used, how much aspirin can be expected to result? Don't let the wordiness of this question intimidate you. We may never have heard of acetic acid or salicylic acid before, and 2,668 grams is quite the quantity, but the underlying concepts are exactly the same. Let's go through this step by step. We have the chemical formulas for these compounds given to us, so let's write a chemical equation. We first have salicylic acid, C7H6O3, and then acetic anhydride, C4H6O3. The anhydride here, by the way, just means that there's no water involved in this compound, which we should remember from our video on nomenclature. Right then, those are our reactants. Our products are aspirin, the technical term of which is acetyl salicylic acid, C9H8O4, and acetic acid, C2H4O2. Just from looking at this reaction, we see that the numbers of carbons, hydrogens, and oxygens are the same on both sides, so the equation is balanced in its current form. Basically what we're doing here is working backward. Instead of trying to find the percent yield, we already have the percent yield, and we're trying to calculate the actual yield and the theoretical yield given a certain amount of reactant. How do we do that? Well, we know that percent yield is actual yield over theoretical yield. Of these, we can't calculate actual yield just by looking at this chemical equation. We can only find the theoretical yield using ideal stoichiometry, the same as we did for the previous example. So let's do that. 2,668 grams of, I'm just going to write S acid for salicylic acid, multiplied by the inverse of the molar mass of this compound, 138 grams per mole, multiplied by the molar ratio of aspirin over S acid, which is just 1/1. We obtain 19.33 moles of aspirin. The molar mass of aspirin, or acetyl salicylic acid, is about 180 grams per mole. 19.33 moles multiplied by 180 grams per mole gives us 3,479.4 grams of aspirin. This is our theoretical yield. Percent yield equals actual over theoretical times 100. So we just need to substitute our values and solve for the actual yield. $86 equals actual divided by 3,479.4, all multiplied by 100. If we do the algebra and solve for the actual yield, we end up with approximately 2,992 grams of aspirin with the consumption of 2,668 grams of salicylic acid. By the way, aspirin itself actually has a pretty long history. It was first synthesized by a German chemist named Felix Hoffmann way back in 1897. Aspirin is now used for a wide variety of different medical conditions and is most commonly applied as either a painkiller or as an anticoagulant. It belongs to a broad drug class known as nonsteroidal anti-inflammatory drugs, or NSAIDs, alongside other well-known medications like ibuprofen. In our next video, Unit 4, Video 1, we will start off a new unit by talking about mixtures. Thank you for watching.